Good morning and welcome to the session Fourier transform. In this session we will discuss the formal definition of the Fourier transform, basic properties and proof, and finally some basic problems. First of all, we will see what is Fourier transform and its inverse. If f of x is absolutely integrable on the x-axis and piecewise continuous on every finite interval, then the Fourier transform of f of x and its inverse are defined as follows. Fourier transform of f of x is f bar of omega, that is equal to 1 by root of 2 pi integral minus infinity to infinity f of x e raised to minus I omega x dx. The inverse Fourier transform is defined like this: f of x equal to the same 1 by root of 2 pi integral minus infinity to infinity. Instead of this f of x we put f bar of omega, that is Fourier transform f of x, then e raised to plus I omega x d omega. See, the input function is f of omega and the variable is omega, so integration is with respect to omega. As an example, let us see a simple problem. Find the Fourier transform of f of x equal to 1 when mod x less than 1, 0 for mod x greater than 1. First of all, we write the formula for Fourier transform. F of omega is equal to 1 by root of 2 pi integral minus infinity to infinity f of x e raised to minus I omega x dx is equal to, now we are going to put the value of f of x here. The f of x has only one non-zero value 1 in the range mod x less than 1. So we put f of x is equal to 1 here. In the range mod x less than 1 can be written as minus 1 less than x less than 1. So the integral minus infinity to infinity changes to minus 1 to 1. Now integral of e raised to minus I omega x is e raised to minus I omega x by minus I omega in the range minus 1 1. When I put the upper limit, I got e raised to minus I omega minus e raised to minus minus, that is e raised to plus I omega by minus I omega. I take a negative from the numerator common, and that negative and the negative in the denominator get cancelled. So I got e raised to I omega minus e raised to minus I omega by I omega. But e raised to ix minus e raised to minus ix can be written as 2i sin x. Using that result, I can write e raised to I omega minus e raised to minus I omega as 2i sin omega. Then I and I get cancelled, so I got the result root of 2 by pi into sin omega by omega. So Fourier transform of this function is root of 2 by pi sin omega by omega. In the next example, we will see the Fourier transform of f of x equal to e raised to minus ax with a and x positive. By Fourier transform definition, f of omega is equal to 1 by root of 2 pi integral minus infinity to infinity f of x e raised to minus I omega x dx. That is equal to 1 by root of 2 pi. Here f of x is e raised to minus ax, integral 0 to infinity e raised to minus ax e raised to minus I omega x dx. Because here x is defined only for positive values, that is why the limit minus infinity to infinity changes to 0 to infinity. Now I take the terms of power together, so e raised to minus of I omega plus a over x dx. Integral of this e raised to function is e raised to minus of I omega plus a by x by minus of I omega plus a in the limit 0 to infinity. That is equal to 1 by root of 2 pi. When I put upper limit, e raised to minus infinity goes to 0 minus, there is one more minus in the denominator, then e raised to 0 is 1. So 1 by minus of I omega plus a. That is equal to 1 by root of 2 pi into 1 by a plus I omega. So next problem, find the amplitude representation of f of t is equal to 5 when minus 2 less than or equal to t less than or equal to 2, 0 for other values, that is t is outside this range minus 2 to 2. So by Fourier transform definition, f of omega is equal to 1 by root of 2 pi integral minus infinity to infinity f of x e raised to minus I omega x dx. Here this function f of t takes the value 5 and 0, so we put non-zero value here in the range minus 2 to 2. That is equal to 1 by root of 2 pi integral minus 2 to 2 5 e raised to minus I omega x. I take this 5 outside, 5 into 1 by root of 2 pi integral minus 2 to 2 e raised to minus I omega x dx. Integral of e raised to minus I omega x is e raised to minus I omega x by minus I omega in the range minus 2 to 2. That is equal to 5 by root of 2 pi e raised to minus 2i omega minus e raised to 2i omega divided by minus I omega. I take that minus common and simplify this like e raised to I2 omega minus e raised to minus I2 omega by I omega. Then as in the previous case, e raised to I2 omega minus e raised to minus I2 omega can be written as 2i sin 2 omega. That I and I get cancelled. 2 into this 5 is equal to 10. So 10 by root of 2 pi sine 2 omega by omega. Here we use the trigonometric relationship between e raised to I to omega minus e raised to minus I to omega by 2ir sine 2 omega. So we got the simplified expression. Next is properties of Fourier transform. As in the case of Fourier sine and cosine transform, first of all we discuss linearity property. If f of x and g of x are two piecewise continuous functions whose Fourier transforms exist, and for any constants a and b, Fourier transform of af plus bg is equal to a into Fourier transform of f plus b into Fourier transform of g. This proof is straightforward. We write the definition of the Fourier transform, and instead of f I use af plus b of g. So that is equal to 1 by root 2 pi integral minus infinity to infinity a into f of x plus b into g of x e raised to minus I omega x dx. Now integral of sum equal to sum of integral. I use that rule here. So 1 by root of 2 pi into a. I take a here. Integral minus infinity to infinity f of x into e raised to minus I omega x dx. Plus I take this b outside. So b into 1 by root 2 pi into integral minus infinity to infinity g of x into e raised to minus I omega x dx. Now this integral is Fourier transform of f, and the second integral is Fourier transform of g. So we can write Fourier transform of f plus bg is equal to a into Fourier transform of g f plus b into Fourier transform of g. This is f. The second property is what is Fourier transform derivative of a function. Let f of x be continuous on the x-axis and f of x tends to 0 as mod x tends to 0. Furthermore, let f dash of x be absolutely be integrable on the x-axis. Then Fourier transform of f dash of x is well defined, and it is equal to I omega into Fourier transform f of x. If we have double dash here, we have I omega square f Fourier transform f of x, like that. We will prove this using basic definition of Fourier transform. Using the definition of Fourier transform, f bar of omega is equal to 1 by root of 2 pi integral minus infinity to infinity f of x into e raised to minus I omega x dx. The place of f of x I am using f dash of x. So Fourier transform f dash of x equal to 1 by root 2 pi integral minus infinity to infinity f dash of x e raised to minus I omega x dx. I interchange these two terms, so e raised to minus I omega x into f dash of x. 1 by root of 2 pi, I use integration by parts. So first function e raised to minus I omega x into integral of the second function, that is integral of f dash, that is f, in the range minus infinity to infinity, minus integral of derivative of the first function, that is e raised to minus I omega x into minus I omega, into integral of the second function, integral of f dash, that is f dx. I take this minus I omega outside, so minus into minus positive, I got plus I omega. Also when we put upper limit here, e raised to minus infinity, it goes to 0, and also f of infinity is 0. So it is a finite quantity. E raised to 0 into e raised to minus infinity, that is e raised to minus infinity goes to 0, and f of x is again 0. So 0 into 0, 0. When I put negative infinity, I got e raised to plus infinity into f of minus infinity, that is again 0. So 0 plus I omega into integral minus infinity to infinity. I interchange these two terms, so f of x into e raised to minus omega x dx. When we multiply this expression by this 1 by root of 2 pi outside this bracket, I got I omega into 1 by root of 2 pi integral minus infinity to infinity f of x e raised to minus I omega x. That integral is actually Fourier transform of this f of x. I bring this term here. So I got I omega into Fourier transform of f of x. So Fourier transform derivative is equal to I omega into Fourier transform of the original function. Next is a remark. That remark is extension of this theorem. That is Fourier transform of nth derivative of f is equal to I omega raised to n into Fourier transform f of x. That means if there is third derivative here, then I omega raised to 3 into Fourier transform of the original function f of x. So instead of evaluating the Fourier transform derivative, we simply multiply original Fourier transform by a power of I omega. Next is Fourier transform of time shifted function. That is a function f of x is shifted by a units. That is Fourier transform of x minus a is equal to e raised to minus I omega into f bar of omega. That means then there is a time shift of a units happened in the transform domain. It is equal to multiplication by e raised to I omega. So we start from the definition of Fourier transform. By Fourier transform, f bar of omega is equal to 1 by root of 2 pi integral minus infinity to infinity f of x e raised to minus I omega x dx. So instead of f of x, I put f of x minus a. Fourier transform of f of x minus a is equal to 1 by root of 2 pi. Instead of f of x, I put f of x minus a e raised to minus I omega x dx. And I put a transformation x minus a is equal to u, and therefore this x is equal to a plus u. So dx equal to du. Then integral limit will not change because x and u moves in the same range. So Fourier transform f of x minus a is equal to 1 by root of 2 pi integral minus infinity to infinity. Instead of f of x minus a, put f of u into e raised to minus of I omega into a plus u. Now we can take this e raised to minus I omega a outside. And remaining term is 1 by root of 2 pi integrals minus infinity to infinity f of u into e raised to minus I omega u du. That part is Fourier transform of f. That is, we got e raised to minus I omega a into f bar of u. 1 by root of 2 pi integral minus infinity to infinity f of u into this e raised to minus I omega a into e raised to minus I omega u du. Here u is the integration variable. It does not contain any variable, so I can take this constant outside. Then e raised to minus I omega into this expression is Fourier transform of omega. So we got the time shifting result, that is Fourier transform of time shifting is equal to e raised to minus I power omega of time shift into Fourier transform of original function. Now change of time scaling property. So if f bar of omega be the Fourier transform of x, then f of ax, that means Fourier transform f of ax, this x is scaled by a units. So it is equal to 1 by a into f bar of omega by a. We are familiar with this result in Laplace transform. As in the case of Laplace transform, we start from the basic definition of Fourier transform. F bar of omega is equal to 1 by root of 2 pi integral minus infinity to infinity f of x e raised to minus I omega x dx. And therefore Fourier transform f of ax is equal to 1 by root of 2 pi integral minus infinity to infinity. Instead of f of x, I put f of ax e raised to minus I omega x dx. I put a transformation to this ax. So ax equal to t, so x equal to t by a. So dx equal to dt by a. As in the case of previous problem, there is no limit change. So we substitute the transformation. Fourier transform f of ax is equal to 1 by root of 2 pi integral minus infinity to infinity. This f of ax changes to f of t. Then e raised to I omega. Then x changes to t by a. So e raised to minus I omega t by a. This t by a is together in the power. Into dx changes to dt by a. I take this 1 by a outside. So 1 by root of 2 pi integral minus infinity to infinity f of t into e raised to minus I omega by at dt. If we have omega in the power, it is Fourier transform of omega. In the place of omega, we have omega by a with this integral representation, that is Fourier transform omega by a. So Fourier transform of ax is equal to 1 by a into Fourier transform omega by a. That is called change of scale property. Next we are going to discuss frequency shifting, that means shifting in the frequency domain. If f bar of omega be the Fourier transform of f of x, then Fourier transform of e raised to ax into f bar of x equal to f bar of omega by a. We have a familiar theorem in the Laplace transform, that is first shifting property. Similar to that, we have here e raised to at into f of t. Instead of that e raised to 8 into f of t, we have e raised to iax f of x. There is a difference. As in the previous case, we start from the definition. From the definition of Fourier transform, f bar of omega is equal to 1 by root of 2 pi integral minus infinity to infinity f of x e raised to minus I omega x dx. Therefore, f bar of e raised to iax into f of x equal to 1 by root 2 pi integral minus infinity to infinity. Instead of this f of x, I write this e raised to iax into f of x. So this, I put these terms together. So 1 by root 2 pi integral minus infinity to infinity f of x into e raised to minus I into omega minus ax dx. If you have omega here, that is Fourier transform of omega. In the place of omega, I have omega minus a. So it is Fourier transform of omega minus a. That means multiplication by e raised to iax leads to shifting in frequency domain by a units. It is known as the first shifting theorem, or simply shifting theorem in frequency domain. The next property is simply application of shifting theorem, that is modulation theorem. If f bar of omega is the Fourier transform f of x, then Fourier transform of cos ax into f of x is equal to f bar of omega minus a plus f bar of omega plus a by 2. This is actually a mean operation, and it is called a modulation operation in signal theory. Here we use e raised to cos ax in terms of e raised to function. Cos ax equal to e raised to iax plus e raised to minus ax by 2. Using this representation here, I got a simplification. Fourier transform of cos ax and f of x as Fourier transform of e raised to iax plus e raised to minus iax by 2 into f of x. I split these terms into 2. So Fourier transform, I take this 1 by 2 outside. So Fourier transform of e raised to ax into f of x plus Fourier transform of e raised to minus iax into f of x. Now we apply a shifting theorem. When we multiply f of x by e raised to iax, it is shifted by a unit, shifted by a unit in frequency domain, that is f bar of omega minus a. Here it is minus ia, so it is shifted by plus a units, f bar of omega plus a by 2. So we got back this result, f bar of omega minus a plus f bar of omega plus a by 2. That is called the modulation theorem. The only thing is we apply cos ax equal to e raised to iax plus e raised to minus ax by 2, then apply the shifting theorem in frequency domain. Then is an important property. It is similar to convolution theorem in Laplace transform. In Laplace transform, we have learned the Laplace transform of convolution is equal to product of individual transform. Here Fourier transform of convolution is equal to not product of individual transform. There is also a multiplication by root of 2 pi. That is the only difference. In the case of Laplace transform, there is no root of 2 pi. In the case of Fourier transform, there is a root of 2 pi. It's a multiplication by this constant, the scaling factor root of 2 pi. Suppose f of x and g of x are piecewise continuous and bounded and absolutely integrable on x-axis, then Fourier transform of convolution G, Fourier transform of convolution is equal to a constant multiple of individual Fourier transforms. That is, the Fourier transform of convolution of two functions is equal to the constant multiple of individual Fourier transform. That constant is root of 2 pi. It's an important theorem in Fourier transform. Okay, thank you very much.